Hello, today we are going to look at recursions. So we'll look at some sample algorithms that are recursive in nature, and we will compute or evaluate the runtime complexity of those algorithms. A very classical algorithm to look at recursion is um, factorial evaluation, which could be also done iteratively, which we'll see a little later. But let's look at what is factorials. So if I want to compute, for example, 5 factorial, it is, it's 1 times, 2 times, 3 times, 4 times, sorry, 4 times 5. 7 factorial is similarly 1 times, 2 times, 3, up to 7, right? So in general, we can say n factorial is 1 times, 2 times, 3 times, so on, up to n. Or we can even say it is n minus 1 times n, right? So 1, 2, 3, n minus 1 up to n. So now, from what we have seen so far, this 1, 2, 3 up to n minus 1 itself could be nothing but n minus 1 factorial times n. Okay? So this is actually what is a kind of recursion, because if I want to compute n factorial, I need to first compute n minus 1 factorial. Okay? So, so I can say, yeah, this is what it is. N factorial is n minus 1 factorial times n. Now, and we have a pseudocode for the algorithm to do that. So if I want to compute factorial of n, if n is 0, we know that 0 factorial is a 1. Okay, so this is like our basic condition, because we cannot keep on going through the recursion. Okay, because essentially, if I want to compute according to this kind of recursive formulation, for example, if I want to compute 5 factorial, it's going to be 4 factorial times 5. So if I want to compute 5 factorial, I don't get the answer right away. I need to first compute 4 factorial. And what is 4 factorial? That is 3 factorial times 4. Similarly, what is 3 factorial? It is 2 factorial times 3. And what is 2 factorial? It is 1 factorial times 2. And 1 factorial is 0 factorial times 1. So we cannot keep on going like that. We know that 0 factorial is 1. So once we know this, we can substitute for 0 factored here, which is 1, and compute 1 factorial, which is 1, and substitute for 1 factorial here, which is 1 times 2, which is 2, and substitute for 2 factorial here, which is 2, and compute 3 factorial, which is 6, and then substitute for 3 factorial, which is 6 here, and compute that to be 24, and substitute for 4 factorial to be 24, and we get this to be 120. Okay, so that is how we compute 5 factorial in a recursive way. Okay, so now if you look at the kind of time complexity here, we have a basic operation which is essentially multiplication. So in each recursion, we do one multiplication, right? So if I want to compute, say 5 factorial, basically the number of multiplications that are involved to compute 5 factorial, we don't need to worry about much of the details. All we can see from here is, if I want to compute 5 factorial, it is the number of multiplications involved will be the number of multiplications involved to compute 4 factorial plus one more multiplication. That's all I need, right? So in general, if I want to compute n factorial, the number of multiplications I need is the number of multiplications to compute n factorial is essentially the number of multiplications to compute n minus 1 factorial plus 1. And this holds good for some n greater than, for any n greater than 0. Because to compute 0 factorial, I don't need to do any multiplication. So this is essentially my recurrence relation. Okay. So now what we want to do is we want to solve this recurrence relation. So how to go about doing that? So from this, I can also say m of n minus 1 is m of n minus 2 plus 1, right? Because m of n is m of n minus 1 plus 1. Replace n by n minus 1. I get m of n minus 1 to be equal to m of n minus 1 plus 1. So it's m of n minus 2 plus 1. So now what I can do, I can substitute for m of n minus 1 here in this recurrence, and I can say m of n is m of n minus 2 plus 1. This term is your m of n minus 1 part plus 1. So it is m of n minus 2 plus 2. Okay. And if you go one step further, you can say m of n minus 2 based on this recurrence. If you replace n by n minus 2, you get m of n minus 2 is m of n minus 3 plus 1. So essentially, I can substitute for m of n minus 2 to be m of n minus 3 plus 1. So I get m of n minus 3 plus 1, which is for m of n minus 2 plus this 2, which is m of n minus 3 plus 3. So start seeing a pattern. Okay, so we have essentially m of n to be equal to m of n minus 3 plus 3. So if I keep going, essentially I can keep going up to m of n minus n, because I know n minus n is 0. So, and I know m of 0 is 0. So if I go up to n here, this should also be an n. So it is going to be m of n minus n plus n. Okay. Basically induction. And so m of 0 is 0. So this is essentially 0 plus n, which is n, and n is theta of n. So I can say m of n is theta of n. So the time complexity for the number of multiplications we do is essentially theta of n. Okay. Now another algorithm. So this is with respect to factorial computation. And another example that we could see here is counting the number of bits in an integer. So if you look at an algorithm to compute the number of bits needed to represent an integer, it's again kind of recursive when the number of bits increases exponentially. So for example, for integer 1, and we are interested in positive decimal integers. So basically things start from 1. So if we want to compute for number of bits for to represent 1, it's just 1 bit. For 2 and 3, it is 2 bits, because 0, 0 is 2, and 1, sorry, 0, 1, 1, 0 is 2. For integer 1, we just represent 1, because we could say 0, 1, but that leading this 0 is not needed. Okay. So that's why it's 1 bit. 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 1, 1, 0, 7 is 1, 1, 1, this is 1, 0, 0, and so on. So if we go up to 15, it's going to be this, right? And then this, you go up to 31, it is, right. So you see here, the number of bits needed, actually the range of integers you can cover doubles for every unit increase in the number of bits. So with 1 bit, we can support only 1 integer. With 2 bits, you can support 2 integers, which are 2 and 3. With 3 bits, you can support 4 integers, 4 to 7. With 4 bits, you can support 8 integers, 8 to 15. With 5 bits, you can support 16 integers. With 6 bits, we can support 32 integers. With 7 bits, 64 integers, and so on. Okay. So now what we are interested is in an algorithm to compute the number of basically the runtime complexity to compute the number of bits. So we are not interested in computing the recursion for the number of bits. What we are interested is trying to come up with a recursion for the underlying algorithm that is used to compute the number of bits. Okay. So if you can see here, the number of bits needed to represent, say, 8 is essentially one more than, like we did for the factorial, one more than the number of bits needed to represent half of 8, which is 4. Similarly, number of bits needed for 15 is one more than the number of bits needed to represent half of 15, which is 7. Of course, we take only the integer part. So the number of bits for any integer n is the number of bits needed for n over 2. Of course, we take only, say, the floor of n over 2 plus 1, right? So that plus 1 is essentially increasing the number of bits by 1 as you go through each range. Okay, and we know that's the basic condition. The number of bits needed to represent 1 is actually the number of bits needed to represent 1 is essentially 1. Now, if you look at this pseudocode, this kind of recursion to compute the number of bits, what is the basic operation? The basic operation is essentially the addition. Okay? So, of course, we can think this division as also a basic operation, because if I want to compute the number of bits for 8, it's basically half of 8. The number of bits represent half of 8 plus 1. And division is more time consuming than addition. But assuming, but still you can see there's only one division and one addition that we are doing. So we can, whatever the analysis we are doing now for the number of additions holds good for the number of divisions too. Okay. So, and since addition is more explicit here, that's why we want to do the time complexity analysis for the number of additions. For the number of additions we do to compute the number of bits needed for integer n is essentially the number of bits. So the number of additions you need, you see, whatever, like the factorial thing, whatever it takes to, whatever the number of additions it takes to compute the number of bits needed for n over 2 plus 1, right? So whatever the number of bits needed to compute the floor of, whatever the number of additions needed to compute the floor of n over 2 plus 1, right? So what the number of additions needed to compute the smaller part, the number of bits for half of the n value plus this one more addition. So that's what comes out to be plus 1. And the basic condition is the number of bits needed, the number of additions needed to compute the binary representation of 1. The number of bits for 1 is 0, because we know that the number of bits needed to represent 1 is 1. So there's no need to do any addition here. Okay. So this is the recursion we want to solve, which looks like this. Okay, this is the floor operation. And so this holds good. The first one holds good for n greater than 1, because we know the basic conditions for n equals 1. Okay, so how to solve this? So this is not in like in the factorial form where we have m of n is m of n minus something. Okay, n minus 1. So if it was in this form, we could say m of n minus 1 is m of n minus 2 plus 1 and so on, and replace m of n minus 1 over there, and we can get m of n to be m of n minus 2 plus 2 and so on. But what we have here is something like this. Okay, so you cannot say a of n is a of n minus 1 over 2, because you see here, if you the range actually doubles, right? Which means the n's actually, it is like increasing in the exponents of 2. Okay, so that's why we have to use a substitution where we set n equals 2 raised to k. Okay, because you see, I cannot say I don't have n minus 1 term, right? So I cannot put something like a of, given that, say, let's say a of n is n over 2 plus 1, if I want to compute a of n over 2, I can say it is a of n over 4 plus 1. That's all I can do. And I can substitute a of n is a of n over 4 plus 1. I cannot go for the intermediate terms n minus 1, n minus 2, and so on, right? And then if I need a of n over 4, it is a of n over 8 plus 1. Okay, so this is the kind of substitutions I need. So you see here, essentially, this is like exponents of 2 that are involved. So that's why we are replacing n to be equals 2 raised to k for some k greater than or equal to 0. If k is 0, n is equal to 2 raised to 0, which is 1. Okay, so that translates to the basic condition, because we have the basic condition to be a of 1 equals 0. So if you want to account for that, we put k equals 0. So a of 2 raised to 0, which is essentially 1, is 0. So a of 1 equal to 0 is equivalent to telling a of 2 raised to 0 equals 0. And then we replace in the recursion n by 2 to the k. So the a of 2 to the k is a of 2 to the k minus 1 plus 1. And this holds good for some k greater than 0, because this accounts for k equal to 0. So now what we have to do is essentially solve the recursion. And now you can see we have a k minus 1 term, and so on. So we can repeat like what we did for the factorial case. So I can say a of k is a of 2, a of 2 to the k is a of 2 to the k minus 1 plus 1. And I can substitute for k minus 1. I can say a of 2 to the k minus 1 is a of 2 to the k minus 2 plus 1. And I can replace a of 2 to the k minus 1 with a of 2 to the k minus 2 here. So I get a of 2 to the k is a of 2 to the k minus 2 plus 1 plus 1. So that is a of 2 to the k minus 2 plus 2. Then similarly, I can replace k with k minus 2. I get a of 2 to the k minus 2 is a of 2 to the k minus 3 plus 1. So now I can replace a of 2 to the k minus 2 by a of 2 to the k minus 3 plus 1. So that is a of 2 to the k is a of 2 to the k minus 3 plus 2 plus 1. So that is 3. So you start seeing a pattern. So in general, I can say a of 2 to the k is a of 2 to the k minus I plus I. Now I can go all the way up to a of 2 to the 0, right? So I can go all the way up to k. That makes it k minus k, so a of 2 to the 0. So then this will be also k. So a of 2 to the k is a of 2 to the k minus k plus k. So a of 2 to the k is a of 2 to the 0, which is 0. So essentially what we have is a of 2 to the k is k. But we know n is 2 to the k, right? So we can replace 2 to the k with n. So I can say a of n is essentially k. But if n is 2 to the k, we can say what? Introduce a logarithm. So if n is 2 raised to k, I can take logarithm on both sides with respect to with the base 2. So that is log 2 raised to k. So log 2 raised to k to the base 2 is simply k, because we can say this is k times log 2 to the base 2. Log 2 to the base 2 is 1, which is simply k. So k is essentially log n to the base 2, and that's what we are replacing here. Okay, and log n to the base 2 is simply that of log n. So the number of additions that you need to compute the number of bits needed for an integer is basically that of log n. Okay.